Hello, my name is Marcos Vinicius, and today I'm going to present my paper, which is named Autonomous Navigation and Collision Avoidance for Mobile Robots. I hope you enjoy. It's a classification and review work. So this work was presented in JAR, Journal of Argentinian of Robotics, in this month, in June, and I'm sharing my presentation that I have done there. So I'm PhD studying electronics engineering at USP, focusing on autonomous navigation and mobile robotics, now for agricultural trucks. And here are some images of my previous project and my team. So what are autonomous mobile robots? Well, they are systems capable of performing tasks in diverse environments, as you can see, and can be static or dynamic environments, but without any human intervention. This is uh, this is the definition of autonomous mobile robots. And in this slide, we can see different applications, environments, and type of robots we have. So here just a video. This robot. So in the left upper side, we have delivery drone that is between the bike. Right side, we have more we have yes, robots. Over in Brazil, parts in a lot of robots. Okay, but what the robots must have to accomplish these tasks? Well, basically, they need to sense the environment and self-locate, and plan the road and operate over this planet trajectory, track this trajectory, sending commands to the actuators. Well, doing this review, we have identified a gap of a unified structure for different types of mobile robots. Each kind of robot and application, they have their own classification and modules integration. And what we wish is to have something more general, in a way that we have better integration, reusability of algorithms, and interconnection. Okay, so given our goal that is to have this unified structure, for example, for ROS2 users, maybe we can use an algorithm that was applied to perception in autonomous underwater vehicle, but could also be reused for autonomous unmanned aerial vehicle, a drone, with a minor efforts. But if you don't have the same classification, the same modules interconnection, it's hard to understand how the robot city is going to reuse that. So our work means to cover this lag. And here are the outline of how we are going to reach the goal. So we have methodology, classification, established techniques demonstration, future trends of robotics, and that's why we have done this work, and the conclusion and discussion. Okay, so let's dive now to the methodology. We conduct a systematic literature review to analyze and synthesize advancements in the architecture designs for autonomous mobile robots. To do that, we focus on seminal papers, in other words, the foundational papers of robotics, the consolidated techniques, mostly widely used algorithms industry, and finally the cutting edge technology and state of art papers. Sorry. So, our review included various types of robots, as you can see in the right side image. An Amazonia robot, indoor robots, drone robots, etc. And we use it in our data as database Science Direct, E3Z Explorer, and database that are very well recognized and very well known for academia and robotics perspectives. You're using these keywords uh, that are very common in robotics, such as path planning, mobile robots, sensors, etc. Okay, so in our review, we found first existing different architectures ranging from simplistic to complex uh, architectures. Many architectures had very unclear modules interconnection, as you can see here, or were too specific for certain applications, confused, generalist, where you don't see the inputs and outputs from a model where how they connect with each other, to abstract, self-oriented, focusing on different aspects such as decision making or computing architecture, or just focus on how the architectures can be reconfigured in hardware terms only, also a paper. But what we wish is reconfiguration architectures for also in software terms, as we depicted in the first slide. Well, what are my inspirational sources? I have inspired myself in the Sense Plan Act, reading the seminal paper of Nielsen. Uh, Also, the introduction of autonomous mobile robot book, which is a very interesting and complete book, which depicts all the phases of autonomous mobile robots. And finally, reading this review of autonomous vehicle, which focus on depicting the main papers from localization to operation in autonomous cars. But now we wish to do the same, similar tables, taking the most important and cutting edge papers, but for autonomous mobile robots. Okay, so that being said, this diagram illustrates the classification of autonomous navigation we have reached into three layers: perception, cognition, and operation, and each layer consists of specific phase crucial for the autonomous function of mobile robots, from environment perception to the trajectory execution. So, in the perception layer, the robots detect and interpret the environment. This involves using variety of sensors, as you can see, such as georeference systems, inertial navigation systems, LiDAR, etc., as shown in Table 1. And data from these filters are processed using common filters like the Kalman filter, extended Kalman filter, Gaussian filters, to ensure reliability and accuracy, as you can see in Table 2. So here we have the main algorithms which depict the sensors, the fusion process, and I have also outlined some one paper for each layer. So here in the word representation, I have selected this article which shows an RFID navigation. So the robots navigate using just RFID sensor inside the industry, so it uses tags and electromagnetic waves As we can see here, there is a filtering process, very not so simple in terms of mathematics, but to do the noise handling, filtering the noise, and adjust the phase difference. And the advantages are no vision system is needed. It's very cost effective. But the drawbacks are that it's not possible obstacle avoidance, and there is limited scope since we cannot navigate with. Uh, you cannot put these tags out in outside environments, in outdoor environments. Just indoor, it's possible to put on the roof or on the walls these tags. Okay, sensor fusion strengthens the robot's ability to navigate through the complex environments. And by combining radar and LiDAR data, the robot can detect obstacles more reliable, which is represented by this seminal paper of Urson, in which the radar map detects the obstacles and the LiDAR map the environment. These maps were fused, and the robot can better navigate over this terrain. Also, we have fusion of inertial sensors for localization. Uh, so GPS, IMU, and odometer fusion, very important for outdoor robots. We have selected, showed papers for this. Now going to the cognition layer. The robot plans its path and avoid obstacles. Path planning involves constructing a graph of the environment, and then we have selected the most common algorithms in this table. Then it uses search algorithms to find the most efficient road. Also traditional algorithms in this table, but also the most recent ones derived from them. And finally, to avoid the obstacles in real time, we have various algorithms employed to navigate around these dynamic obstacles, ensuring safe and efficient environment. So here we select a paper which shows this is XXL, the composition method of table 1. So a path is created in this free area, and uh, a more advanced paper, more recent paper, which depicts 3D path planning. For obstacle avoidance, this paper of autonomous underwater vehicles is very interesting. It uses grid cells, so each cells here in this 3D environment is a neuron, and it's defined a weight for each cell based on how close it's from the target and how close it's from an obstacle. So assigning a high value if it's closer to the target, and the small value if it's closer to an obstacle, and then the robot can avoid dynamically these obstacles. Finally, the motion control, we have depicted different actuators from underwater to Mars exploration. Selected the most common papers from controller, and finally the trajectory execution methods. Then in motion control, we have this paper selection. That is how the controller maintains the autonomous vehicle in the lane using vision methods along with control methods, and the trajectory tracking and the trajectory execution method, that is offline planning, where the robots cannot avoid obstacle, just use dead reckoning. To episodic planning, where the robots map needs to remap the environment and starts in every cycle. Hybrid layer switching, where the robot parks and can switch from parking to autonomous rail operation. And finally, real-time replanning in race cars competition. So Now, okay, so the video was is cut because in the Congress I didn't have I didn't have many time to explain, and here I am explaining more calmly. Uh, then I'm not running too much, so I'll track here the where we have stopped. Let me see. Well, I think I stopped it here. So this is the adaptability from the in the environment, low here to the high, and the complexity from more slow vehicle to complex and dynamic environments, which is a race car competition or in a urban traffic scenario. And then we can go now for the techniques, the well established techniques, which are basically SLAM for indoor robots, but also their visual SLAM for outdoor robots. So let's see here this video. Usually they rely on odometry and LiDAR. The indoor robots can correct its errors fusing these sensors. And the drifts or the displacements, offsets from real position is corrected. So we have selected scan matching algorithms in our papers, Gaussian-based model, image classification, simultaneous and localization, and mapping based algorithms. For example, we have selected this paper which fuses visual data as odometry and LiDAR. So we have uh, this visual map of environment, and the robot can follow the path, can detect where it's a path available to plan and to localize in this city. Our vision methods, we have read a lot of papers which use it OpenCV and YOLO for image processing, real-time object detection, and they rely on neural networks for prediction to predict the obstacles and then sending these obstacles to the predictor and decision making model to decide what to do with this data. So I have here just an example: a chair being detected, laptop, monitor. These tools are very reliable and widely used in the perception with vision systems. We have also segmentation techniques, which are very common on robotics. So, for example, if you segment uh, uh, enough road environment, and you don't wish your robot calculates a path over the grass, so this grass is filtered out with Gaussian filters, and and then the computer load, the computer processing, it's going to reduce because the robot will just calculate over this straight path here in brown, so saving resources. And of course, making the robot calculate the path correctly, not in undesired areas. Also, the same we have for different robot, which is a legged robot. So the left leg of the robot is here in green, and the right left is represented by this blue rectangle, and this orange color is reflects the high height obstacle, and then if the robot this obstacle, this height is converted using transformation in inverse kinematics. So the robot understands that it needs to move its legs upwards to overcome these obstacles and step over it, and finally traverse it. So if the area is a plane, this gray plane, the robot just moves normally without step too much over in, and that's the idea of segmentation. So we show different applications here. Finally, we have recent advancements in autonomous mobile robots, reading the most recent papers, which are basically adaptability across environments. So we have multimodal and hybrid vehicles. They are being produced more constantly. Are still kind of innovation. So the robot can fly and walk, for example, or can navigate underwater and in the over the land. Also, 5G communication, cybersecurity, and artificial intelligence in the loop. So improving all the phases from perception to operation. So let's see some videos. Okay. This robot with Leonardo is the drive is not implemented. This one there. Leonardo. Okay, great. Let's go to the last video. On the left side, we have this 5G communication and the V2X and V2 structure and communication facilitate the navigation inside the city, which are very chaotic. This makes it very carefully traffic lights to avoid it. And with the right side, the robot running its errors, running not better it's like power and that's future and what is already present here. Okay, so let's go to the next slide. Finally, the conclusion. So our contribution to the recent uh, classifications are in terms of standardization. So we can have more easier implementation, reuse of algorithms for different type of robots, as you could see. Of course, we cannot use, for example, a specific algorithm of autonomous underwater vehicle for autonomous vehicle because they they move in over different environments. One moves in 3D, other in 2D, but you can use maybe similar algorithms for 3D environments or or for example visual Islam you could use or just readapt the algorithm for an autonomous vehicle to an underwater platform, and that's the idea. It's to promote this holistic classification because the industry relies on standards to provide scalability. Otherwise, it's hard to to have scalable production, and that's why the importance of follow a standard and understand if we have if our robots have all these models, which algorithm it's used for a respective model, and not have every robot with a different architecture. That's not the ideal. And as we could see, we have now hybrid robots, multimodal robots that switch layers, switch behaviors, and this unified architecture. We believe that's going to contribute a lot. Also have done this extensive review in parallel with that autonomous vehicles, autonomous cars review. We have included papers from all the layers with depicting all the phases. Of course, if you wish to read the article, be happy, and you will see there a lot of different strategies for navigation, for localization, for perception, and it's very valuable articles we have selected in those tables. Each number means an article. We hope we will promote flexibility in the developing of these AMR, autonomous mobile robots, to deploy to different robotic systems in a modular way. So we can just remove a module from a localization, an algorithm, and put another one, and you will not affect the overall the other models. But also flexibility and better understanding in for educational resource for new robotics, new students. We think that that classification is very clear. Finally, the discussion I have invited in the Congress everyone to discuss, provide feedback and critics of the proposed classifications. And also here, if you wish to comment this video, criticize, give ideas, also collaborate in some project. The Congress, they criticized the article that it should have a robot in which I have applied this classification, all these models, all these algorithms, and they are correct. So if you wish to create a robot and we could do something together and provide a GitHub with this classification and reusability of models, and we are encouraging this collaboration. So my references from this presentation are here. Of course, the references, not all of them from the article, so you can see all the references in the article itself. We have almost 100 references. Finally, open to questions, and my acknowledgements to my advisors from Master and PhD from UFIX and USP, Leopoldo and Roberto Simoni, the University of Santa Catarina, where I have done my master, the USP, where I'm doing my PhD, the University of Buenos Aires, which accepted the work and received me very well, which was very nice Congress, very good Congress in terms of quality and roboticists, and the funding agencies, FAPESC and CAPS, which paid my scholarship and my contact if you wish to reach me in LinkedIn. Thanks very much.